Hi, I'm Ekaterina. I'm a last year, hopefully, PhD student. My home institution is the Leibniz Institute for Astrophysics in Potsdam. I'm here as a visiting scholar at the American Museum of Natural History until June next year. So if you want to talk to me in person, 6 months ago, I'll bring you a brief story about finding nothing and almost doing it all wrong, but on a very interesting object. So remember AUMIC, it's the most actively flaring exoplanet host in Kepler and TESS, which is exciting because we haven't known that it is an exoplanet host for the last 2 years or so, and actually has 2 planets, which is cool. They do actually transit somewhere in here. Transit. It's a little bit hidden. Do I have a pointer? No. Oh no. That this guy is the pointer. Yeah. Woo, woo. Okay. Here is one transit, I think. And so this is a light curve from TESS. And you see that time flux has a rotation period of about 5 days. You see the spots and you see flares all over. So I've looked at all exoplanet hosts and I found about 1,500 flares. The 2 light curves of AUMIC and TESS of 50 days of observation have 200 of those. So it's an interesting talk. So what I'm interested in is magnetic star-planet interactions, and in particular flaring star-planet interactions. So the interesting thing about AUMIC is that it has predicted that it will have at least, could have planet-induced radio emission. It depends a bit on its low mass loss rate. So if it's a high mass loss rate, magnetic field lines will be open, nothing, like all the particles will be just thrown out, nothing can come back. But if you have low mass rate, you can have closed magnetic fields and actually material can fall back onto the star, which can trigger flares. So what we expect is some periodic recurrence of star-planet interaction triggered flares. So this is what I was looking for. And this is the story of how I almost did it all wrong. So the classic statistical tests to distinguish uniform distribution for something that is not uniform is a Kolmogorov-Smirnov test. So what I expect is to see no dependence on the orbital phase of the planet or the rotational phase of the star in terms of the number of flares that occur. So I did this test, and you see on the right, the significance of the detection is 1, 2, 3 sigma, and you see it's all over the place. And it depends on what starting phase of the orbit or the rotation period I choose. So I can do it very wrong. I could get, if I tweak it, I could get a 3 sigma detection. So please be cautious with Kolmogorov-Smirnov. What's better is an Anderson-Darling test. So the problem with Kolmogorov-Smirnov is at the edges of a distribution, it downweights the difference and it overemphasizes the center of a distribution. And the Anderson-Darling test corrects for this. So this is what you see here, which is much cleaner. You still get, well, in some cases, something like a 2 sigma, but the picture is much more clear. So this is the story of how we found nothing and almost did it wrong. And I think that's all I wanted to say. Thank you.
Thank you. Questions? Right on time. Yeah, go ahead, Murphy.
Is this Anderson-Darling test strong enough to rule out planet interactions at this point, you think?
It definitely rules out that we see them at like above the intrinsic flaring at this point. So it's a tricky question. So I think what we need to do, so the problem with all statistical tests that they are constructed artificially. And what we actually need to do is to go for all the other planet hosts and do the differential comparison and see if there is actually any statistical difference between those, and then go from those that have perhaps something statistical going on, and follow those up. But yeah, it might be, we're wondering what might be the reason. It might be really instrumental, but it might also be physical, like this mass loss rate thing. But it's hard to tell. So we only can say that in the flaring, there is nothing yet.
Thank you.
Longer.
Okay. Apologies to folks who have more questions. We do need to move on, but lucky for you, we have time at lunch and later where you can ask Katerina more. Let's thank her, Katerina again while Joel comes up. Let's go forward.
Hi everyone, I'm Joel Zinn. I'm an NSF fellow at the American Museum of Natural History. And today I'll talk a little bit about a project that I've been thinking about recently on luminous giant astroseismology. The motivation here actually comes from galactic physics. So if we look at stars of a given age, a stellar population of a given age, their velocity dispersions decrease with increasing galactocentric radius. We think we understand this because the potential of the disk is decreasing as we go out into the outer disk. But with some recent data, we've seen this kind of uptick. And to really get a handle on whether or not this is real, the data is a bit few and far between. We need, as always, more data and more accurate ages in the outer disk. So the best way to do this in the outer disk is with astroseismology. This gives accurate and precise ages for stars, in particular red giant branch stars, which we can see throughout the disk. Unfortunately, our existing astroseismic samples are limited to the vicinity, solar vicinity, so Kepler within about a kiloparsec, and even the largest astroseismic data set in the literature, K2 Galactic Archaeology Program, is limited to within about 5 kiloparsecs. So you may ask, why is this? So indeed, for lower luminosity giant branch stars, astroseismic radii are very well calibrated. When we compare them to fundamental Gaia radii, they agree within about 1%. But for more luminous stars above about 30 arson, which we could see in the outer disk, this starts to break down. And so with more recent data, we're seeing that this is about 100% effect at the tip of the red giant branch. So this could be due to a couple of things. These are the astroseismic scaling relations, which give us radii and masses for stars. This is important because red giant masses give us the ages of those red giants. So there could be problems with either the nu max or delta nu part of these scaling relations. These are quantities that we can measure from time series from space-based missions like Kepler and TESS. And I've been thinking a bit about what could be going wrong with delta nu. Delta nu depends a bit on stellar models, and the way we compute delta nu from stellar models assumes that the entire star is adiabatic. And this is an increasingly bad approximation as you go up the giant branch. So if we spend a little bit more computing time computing delta nus in the non-adiabatic treatment, we can then compare it to how we normally compute delta nus under the adiabatic approximation and come up with how much of this radius error and therefore the mass and age error can be ascribed to the adiabatic approximation. And we see that it increases with increasing radius, which we expect because the star is less and less adiabatic. For stars around the red clump, this is the low luminosity, low-ish luminosity regime. That error is about 2%, which is consistent with Gaia radii. But for the red giant branch tip, it only gets up to 10%, no matter what mass or mixing length alpha you choose, shown in different panels here, or metallicity shown in different colors. So that still leaves many tens of percent error unaccounted for. So the good news is that delta nu is probably not the issue, and we can correct that. So that leaves nu max, and the good news there is that since it's a one parameter problem now, we can use Gaia radii to basically empirically calibrate the radii and therefore get calibrated new maxes for masses and therefore ages. So with this sort of technique, with luminous giant astroseismology, we'll be able to increase the volume probed in the galaxy by 1,000 to 30,000 fold, especially thinking toward Plato and Rubin observatory data. So I'm looking forward to continuing along these lines and other lines listed here. And if you are interested in that too, please do reach out to me. Thanks.
Thanks, Joel. Do we have questions? Ruth has a question.
So with luminous giant astroseismology, like you have a volume there. What kind of distances could you go to with Rubin, say?
Right. So for Rubin, you can get up to 150 kiloparsecs. So that would include resolving individual giants in most of the known dwarf satellites. With Plato, it's limited to within about 50 kiloparsecs, but you still get the large and small Magellanic clouds.
Yeah, Catherine.
It's fun. What sort of sample size can you get if you need to have astroseismology data that you can do astroseismology with? What are the prospects for that at large distances?
Yeah. So at least with I'm expecting a sample of about 100,000 stars available with tests. That's not including Rubin Observatory. I haven't done the numbers for Rubin, but it'd be much more.
Okay, let's thank Joel one more time. Kai is up next.
And that's the pointer. Very good. There we go. Okay. So this is work that a graduate student at Drexel University, there we go, Sean Lewis is leading, and a number of other people in the TORCH group have been supporting it as well. So what is TORCH? It's a way of, it's a software framework that takes the Flash MHD code and couples it through AMUSE, the Astrophysical Multipurpose Software Environment, on a time step by time step basis with other codes such as N-body or stellar evolution codes to allow us to combine the evolution of gas and of stars treated as true N-body particles in order to follow the evolution of star clusters from when they were but a gleam in a molecular cloud's eye, all the way through to through their evolution ultimately. So Joshua Wall's thesis was devoted to that coupling and using a bridge module to move from the adaptive mesh refinement description of gas into the gravitational particle description of various N-body codes like pH4 or now Wang's PTAR code. That allows us to couple these two modules together. As an example of that kind of work, this is work that Sean is preparing for publication with us. This is the same initial conditions. The only difference between these four models, 4.5 megayears after collapse star formation started, is that in this model, we just took random stars from an IMF and inserted them in regions of collapse, so following a sync particle formulation. But in the other three models, we chose to put in by hand an early massive star of 50 solar masses, 70 solar masses, or 100 solar masses. So this is specifically asking in a cluster starting with around 10,000 solar masses of gas, How important is the question of whether a early massive star appeared for the subsequent evolution of that cluster? And the answer we can already see morphologically is that it's the difference between a centrally concentrated cluster and isolated groups, because that early massive star blows away the surrounding gas with its wind and then, much more importantly, its ionization. If we look at quantitative questions, we can see that the cumulative stellar mass is much higher in the fiducial model than with prompt massive feedback from any of the stars. And the gas total energy pops up as soon as we insert the massive star at 2 megayears to positive values. And that explains why there's so much less feedback. So this is an example of the kind of thing we can do with this framework. However, this framework is open source. Amuse is open source, and we have made our modifications open source. And so we certainly invite anybody who is interested in working with this sort of tool to join us. We have user group meetings every Monday, and there are many possibilities for things that can be done with it. We already have 4 or 5 graduate students working on this: Claude Cornelier-Cloutier, Brooke Polak, Sean, of course, William Farner, and some other folks. And there it is. Questions?
Thank you. Do folks have questions for Mordecai?
Ruth first, then we'll move down.
Yeah, if as long as it's quick.
I
But
was just
Ruth,
wondering,
take it away.
yeah, do you see signatures of the primordial angular momentum in the gas? Do you see signatures of that lasting for a long time in the stars?
So we are not yet tracking the angular momentum of the sinks, but that is something that we should is pretty much a question of someone sitting down and doing the accounting for it. All the pieces are in place. We're absorbing gas into sink and following properties. So it's a question of adding one field to the sink structure. We hope that someday someone will do that because it's clearly of importance. Rachel?
Maybe I missed something. What's happening at 4 megayears in the fiducial model?
That's when a massive star happened to form just
Just
from
okay,
the IMF.
not one that you put in, but okay, thanks.
Exactly.
The mass dependence on the individual stars. What does this? What does it have implications for metallicity, enrichment, and mixing beyond just dwarf gas? Anyway,
Yes.
where you want with that?
So Brooke Polak is trying to do the same sort of model for like hundred or hundreds of times bigger clouds, and with the goal of following like metallicity contributions and mixing between subclusters and things like that. And she's now running preliminary low resolution models, but with the intent of getting to high enough resolution to be able to say interesting things about that.
All right, let's thank Mordecai once more. And Mark is up next.
Great. Thank you.
Hello, everyone. My name is Mark Popenchak. I'm a graduate student at the Graduate Center and Hunter College, but working with my advisor, Jackie Faraday, at the American Museum of Natural History as part of the Brown Dwarf New York City group. Besides that long list, I'm also involved in Astronomy on Tap. So you've all been advertising yourselves as speakers for potential Astronomy on Tap events. You didn't know that, but you have been. And so I might contact you afterwards. But also, if you're interested, we're trying to be moving back in person starting next year. I'll just quickly highlight work from my last paper, which was looking at M-dwarf rotation rates across age. This plot was particularly looking at rotation period distributions, as well as H alpha activity for M-dwarf stars in a variety of ages, and then also looked at them in terms of Gaia kinematics for field stars. So if you want to talk about that, please find me afterwards. But I'll speak about our current work right now. Is that the motivation behind it is that spatially distant associations near the sun, so in our local solar neighborhood, are spread out across the sky, but in a kinematic space, many different populations seem to fall very close to one another. And so if you want to investigate stars that are all across the sky, a good way of doing that right now is with TESS. And so we have within our groups and reaching outside of BDMIC as well, assembled a kind of test squad that investigates the similarity of the rotation rates of these different associations. We use Google Collaboratory code that was created by Jason Curtis, featuring Soha Hattori's unpopular detrending algorithm. And it was designed for high school students. And so as part of this, I've been able to work with a couple of shrimp cohorts at the museum. So if you're interested in education or outreach efforts at the museum, also please feel free to find me afterwards. And so in particular, I've been looking most recently at Takor, 45 million year old association. And this is the rotation period diagram. And so we've got color and spectral type running along the x-axis, and the rotation periods of these stars, the yellow ones being Takor and Pleiades and Persepi in the background to kind of give you some comparison for ages. While most people focus on this emergence and then location of the slow rotator sequence, as it is a nice correlation with age, I also am looking at the rapidly rotating M's because that's what my first work was on. And also it's the closest thing to brown dwarfs on this plot. Some of these are brown dwarfs, so that lets me stay with brown dwarf New York City. But in particular, with these rapidly rotating M's, at these young ages, there are some really interesting objects. There are only a handful of them. They're called complex rotators. And so I'm showing some light curves here on the right. These are phase-folded light curves, so only showing the repetition of their cycles of rotation, and the different colors are different orbits of TESS. But what you might notice is that there are some really fine structures within here, and that they persist throughout each orbit of TESS, and so over many cycles of rotations for these objects. This is, it's not really known why this is happening. You would expect these short timescales of like tens of minutes to just a few hours to moving along. And so one leading theory, or a couple of leading theories, is that this is either co-rotating clouds of material out at a Keplerian orbit, so like kind of like geostationary orbit satellites, but for clouds of materials that are causing these dips, or perhaps star spots with a misaligned spin orbit dust ring. And so while these things have been known for several years, and I list some sources here to follow up on if you're interested, what's nice with TESS is that now with cycle 3, we're able to see how they've changed. And the fact is some of these objects have changed. None of them, while some major features might seem similar, they all have kind of changed shape. And so it's a nice result to be able to talk about and how this could inform the theories of what's going on with these objects. And so, yeah, it's interesting to look at these young objects and continue to look at their rotation periods. Thank you.
Thank you. Questions? Yes, question.
Is complex rotator only for amps, or they're just like any young stars?
Yeah, they're only seen in rapidly rotating young amps. So all sub 1 day periods, and only there were a few seen in the Pleiades, but otherwise it's got to be younger than 100 million years.
Yeah, Alexander, question.
It's really interesting. So if they're co-rotating, though, wouldn't you expect some sort of magnetic effect, right? Because
Yeah.
where else is the co-rotation radius?
Yes, I'm definitely not a theorist, so I'm not going to be able to fall one way or another. I definitely lean more towards the there being a dust ring, and like the change, certainly the change from cycle 1 to cycle 3 could maybe due to precession or something, and so like the disks not occulting as much. We would expect the star spots to exist on this timescale, though. We have a lot of other M's that do keep the same shape to their light curve from cycle 1 to cycle 3. So the star spots could be living this long.
Are there any other diagnostics that you could connect, like magnetic activity on the surface, to the actual modulations?
That's a very good idea. Yeah, we'll look into that.
Okay, let's thank Mark one last time. And Jackie can come on up.
Okay. Okay, I'll get it wrong, I'm sure. All right. Hi, everybody. So I'm going to take my 5 minutes, 4 minutes, whatever this is, to give you a potpourri of projects that we work on. This is a picture of my group, the Brown Dwarfs in New York City group. You just heard Mark talking. He was talking about projects on the high mass end of brown dwarfs. Daniela and Johanna spoke in the last session on low mass end of things. We work on everything that comes in between what you define as the word star and what you define as the word planet. And hopefully you struggle with the word planet as well, because it is a poorly defined object, not just at the Pluto mass end, but also at the high mass end, as you might have kind of gotten an idea of from Daniela's talk and even Johanna's talk. So we work on the objects that kind of bring everything together, brown dwarfs. This is the team. There's a lot of us. I think all of our talks are today, but anybody on this slide, you can ask other questions about projects that they're in. So highlight projects. Told you I was going to do it wrong.
Sorry, can you speak closer to the microphone?
Oh, can you not hear me? I feel like I'm shouting.
For the people on Zoom, thank you.
Okay, yes. All right. So a highlight of topics that we're working on, I'm using space telescopes as kind of a definition of some of the really exciting things that we're doing. I'll start with a citizen science project that I co-founded a couple of years ago called Backyard Worlds. It aims to find cold, compact sources that are near the sun that were missed through regular searches. And when I mean cold, compact sources, I mean objects that are barely warmer than Jupiter, that hang out at the boundary where you'd have trouble calling them a planet or a brown dwarf because they're just a couple of times more massive than Jupiter. We have not found one closer than the sun, than the closest star yet, than Proxima Centauri, but I stand by that I think it could still be out there. But we have found several of these extremely enticing, very close by objects. And what we're doing with the James Webb Space Telescope, which most of us know is launching in 3 weeks, less than 3 weeks, is that we've won some cycle 1 time to go after several of these brand new objects, some of which discovered by citizen scientists, that are the coldest compact objects that we currently know form through the star formation process, so that we can look at their atmospheres, so that we can figure out what kind of clouds they might have, what signatures in their atmospheres might be there to tell us also something about their formation process. We also have Hubble time right now to go after cold compact sources that I don't really think any of them are closer than Proxima Centauri, but it's always a possibility. We found just very close by, fast moving objects that are extremely faint at the edge of what's currently detectable, discovered by citizen scientists. And then we go to the higher mass things, which you just heard Mark talking about, which at the high mass end, you end up with these objects that are right at the boundary of stars and brown dwarfs. But then when you go to the fainter ends, if they're young, they can actually also beat down the boundary of the word planet, because cold ones that are old are low mass, but Young ones are hot in low mass. So we go after those, and TESS can even see a couple of those. So we use TESS to go after what their rotation rates are. And then we use Gaia for everything. Okay, so this is a hot potpourri of some of our projects. There's lots to collaborate on with anyone in this room. And I want to end with two different things that I always want to highlight for New York everybody's, which is what this room is. Number one is, as a reminder, I work at the American Museum of Natural History within the Hayden Planetarium, which all of us that work there sit above the Hayden Planetarium. I use the Rose Center or the Hayden Planetarium on a regular basis to visualize various data sets that I have. Gaia data sets are great for this. This is an image of me presenting of all of the stars in Gaia that have been mapped by apogee or GLA, and they're color-coded by chemistry. It's a really fun, exciting place to be. And so if you've got a data set that you want to see visualized, let me know. Call me up. Let's discuss. Maybe we can play with it inside of the dome. I'm going to be in there later today. I've been given permission to give an extended invite. We're going to have some very exciting stuff in the dome today at 4 o'clock. There's an astronaut from the Inspiration 4 mission that's coming. Neil is going to moderate, and we're going to take some people on a tour from here out to Mars and highlighting space exploration. Especially want students, if you want to come to me after and let's talk. But other data sets, come to me. I would love to see your data sets in the dome. And last, a project that is dear to my heart, recently funded by the Alfred P. Sloan Foundation for a planning year. It's called 2030 STEM. And this is focused on diversifying STEM in this in the era that we're in. I think it's extremely critical that we all look around a room like this, and make sure that we see representation across all walks of life. And 2030 STEM is a 10-year project where we're hoping to raise funds for a new fellowship that would be offered to underrepresented groups in science. In this planning year, we are going to be hosting a number of salons that are going to be getting at DEI issues. The first one is on social media and how it helps to amplify those underrepresented groups in science. And at the end of each salon, we're going to have a white paper that'll come out. The first one's in January. I'd love to talk to anybody that wants to know more about that too. That's all. That was a lot. Thank you for listening.
Thank you, Jackie. All right, we have time for maybe one or two quick questions. Catherine.
About the other topics for the salons for this.
Yeah, one of them is going to be on bridge programs and the success of bridge programs, how they're working. Another is on fellowships directed at BIPOC across URGs in general. The fourth one, we're still fleshing out. Those are the three main ones. So the first one, January 27th and 28th, is the topic itself is being fleshed out, but we're trying to bring people across not just STEM, but also industry into a room together so that we can see how the full spectrum of where researchers end up go. So industry may very well be our fourth salon topic. We just don't have that one planned out yet. We have the full year. We only received our planning year grant 1 month ago. The funds arrived 2 weeks ago.
Okay, thank you, Jackie. This is great. Next up is Ruth.
Thank you. Hello, I'm Ruth Angus. I'm a curator at the Natural History Museum. I think I'm rounding out the Natural History Museum people for this session. I also have an appointment here at the Flatiron Institute, CCA. I'm an associate research scientist, and I'm an adjunct professor at Columbia as well. And I'm talking sort of generally about my bread and butter research, and I'll highlight some of the results we have in our group. Some embarrassing pictures, they're not embarrassing, lovely pictures of some of the people that I work with are displayed along the bottom of the slide here. So this is a movie created with data that Lucy Liu provided in her last paper. So this shows rotation period of stars, main sequence stars, as a function of their effective temperatures. And one of the main things that I work on, one of the things that I'm interested in, is understanding how we can measure the ages of main sequence stars more precisely, because this is a really difficult problem. Most main sequence stars just don't yield up their ages very easily, but their rotation periods really change quite drastically and significantly over time. And Lucy's data really nicely reveal that. So what Lucy did was she took a data set of measured rotation periods from the Kepler spacecraft, measured using data from the Kepler spacecraft. I can't point in the top left corner. There's a logo in the top left corner for Kepler. And what Lucy did was she calculated kinematic ages for these stars using the velocity dispersions of each star grouped with its nearest neighbors in parameter space. So stars that look similar, have similar rotation periods, are in similar positions in the color magnitude diagram. And she calculated kinematic ages for these stars. So we're able to make this incredible movie which shows how the rotation periods of stars evolve over time. The rotation periods of stars lengthen as they get older because they're spinning down through their magnetized stellar wind, which means we can turn this around and use the rotation periods of stars to reveal their ages, which is really critical for a number of projects that we're interested in. We want to unravel the formation history of the Milky Way. We want to understand how planets and planetary systems change over time. And here's just a sort of cartoon of a few examples of things we've learned from ensembles of rotation period measurements. So for example, we learn how stars spin down over time. We learn how their interior angular momentum is distributed, how the cores and the envelopes spin down separately. We learn how the magnetic fields of stars change over time, how their morphology changes, how their strength changes. And we've also learned how planets change over time. So Trevor David led a couple of papers that show that sub-Neptunes turn into super Earths. And he did that using stellar ages. Okay, so that's sort of what I wanted to say about science. I also wanted to highlight a few things that I work on relating to science communication. So I'm involved in a number of projects that are bringing science onto the stage and onto the screen and onto the page. So in particular, I just wanted to highlight this program that's called Microcosms, which is an NSF-funded program at the museum where we are going to bring astronomers and playwrights together to create new work, devise new work, which we will hopefully have readings of at the museum. And then there are a few other projects here that I'm involved with, staging science and science communication through film and books. Please feel free to ask me questions about any of these things. I'm very happy to talk in more detail about any of them. Great.
Thanks, Ruth. Do folks have questions for Ruth?
I can talk more about some of these things.
I was actually gonna ask about microcosm. So is this quite new? And if people are excited about joining, now is the time to get in on it?
It's new, so we're probably going to be recruiting astronomers for this next fall. It's still very much up in the air, like this is the planning year for us as well. So we don't know exactly what it's gonna look like, but we'll definitely have astronomers involved, and we'll have playwrights involved, and we'll create incredible work, hopefully.
That's fantastic. Other questions? Let's see, all the way in the back, Jackie.
Ruth, back on Lucy's, your movie of the generated rotation rate. So can you just say something about the M dwarfs disappear? So are you going from test to Kepler here?
There's no test data here.
Oh, okay. So it's all Kepler?
All Kepler. So we're hoping to add data to this with tests, and the test data will really expand this to the right.
Right. Okay.
Yeah. The M dwarfs are just from clusters.
That
You
makes
can see them at the young ages and then they disappear.
okay.
Didn't observe many M dwarfs.
Okay, one final question. Behind you, sorry, Joel.
Related to this animation, can you talk a little bit about the scatter around 5,500, 6,000 Kelvin as you go later in time?
Oh, yeah. So you can see like a little sprinkling of stars that kind of appear at late ages. Those are the subgiants. So they tend to be older. They have a really broad spread in rotation period, which is caused because some of them are very young and they're rapidly rotating. Hotter stars, they're evolving in a different way. Their envelopes are expanding, so they're slowing down because of conservation of angular momentum as well as magnetic wind breaking. So that they're sort of doing their own thing.
Hi, I'm Zach Richards. I'm a faculty member at Suffolk County Community College. I'm also associated with AMNH and the Institute of STEM Education at Stony Brook University. And today I'm going to talk to you guys about predictors of astronomy performance for your students so that we can identify at-risk students of failing your astronomy course to, one, increase interest in astronomy, and two, increase STEM retention, which is quite a large problem. So typically, if you have teaching responsibilities and you're teaching astronomy, most likely you're teaching in a non-majors course, and in that, your course probably looks something along these lines, where you have approximately 96% of your students who are non-STEM majors, about 28% who have taken a developmental or remedial math course, and about a fifth of your students probably repeated math at some point in their higher education career, indicating that they might not necessarily have the skills to be successful in a STEM course. And that's also a problem because, well, our STEM workforce is in high demand for students or for jobs. So I decided to create a model with both demographic variables as well as academic variables to find how important they are with predicting the astronomy grade, which was decided to be a dichotomous variable as the ABC rate or passing, or DFW as failing. And what I found out was that the most important predictors were the students' GPA, their math GPA, their major, so whether it was STEM or not STEM, the number of astronomy courses that they've taken, if they took a developmental math course, or if they repeated a math course. And which brings us to the first interesting result, is that the demographics were not important in predicting student performance, which means that in an intro level astronomy course, everybody's at an equal playing field. So for this, I ran a logistic regression and a decision tree. And so what came out of this was that the three most important variables were their GPA. So students who had a higher GPA were more likely to pass. Students who took developmental math or repeated their math course were less likely to pass. And here there's a little confusion matrix of a test set that I ran this on. The overall accuracy of this model was 74%. And here, from the decision trees, it also says that cumulative GPA, when we calculated the feature importance, was the cumulative GPA, whether or not they took developmental math, and their math GPA. And from this, the decision trees had an accuracy of about 70%. And I'll be looking to improve the accuracy of this in the near future. I just happened to get my hands on the data set not too long ago. So this is just a rough look at everything. And So what we can conclude from this is that the two most important features to predict student performance is their GPA and whether or not the student took developmental math. And so some recommendations for those of you who teach an astronomy course, when and if you decide to use math in your course, spend more time focusing on conceptual understanding of the equations before just throwing the students straight in, because they might not necessarily be able to grasp that, and make that relevant to them so that we can increase STEM retention and overall interest in astronomy. Thank you.
Thank you, Zach. Do we have questions? Looks like Mordecai has a hand.
What was the data set? What was in other words, what's the student population that you're studying? Is this national or institutional?
Yeah, so this was taken as an institutional database from a New York State community college. So while this is a community college, I will add the side note. So approximately a little bit more than 50% of all students get into a community college at some point. So even if they did not necessarily take astronomy at a community college and they took astronomy at a four-year institution, they would still fall into this.
Do you have any prospects for expanding your data set?
So this data set, and this is a pretty large data set over 4 years of institutional data, so it's quite large. And in this, there were about 2,500 students who took astronomy at this institution. So I'm going to continue doing more in-depth analysis on this data, and eventually there are plans to expand this for concrete analysis for four-year institutions as well.
Great.
Jillian, and then I'll come over to Joel.
Hey, Zach. I'm wondering about the amount of math that is in the course, because in my experience, introductory astronomy courses can vary a lot, from having almost no math and being super conceptual to having a more heavy algebraic load. And so what is the level of math in these courses? And do you expect these results to be different if there's, for example, no math or more math in an intro astronomy class?
So in the institution where I took the data from, the prerequisite is Algebra 1. And more often, I can't speak for because everybody at the institution does in fact teach it a little differently. I would expect that it would be the same across, but typically it would be just basic algebra, maybe some scientific notation in there as well. But I would expect that to be it would expand across whether or not there was less math or more math. Unfortunately, I have no way of getting this information. Yeah, so that I could actually, well, I'll see if I can get that information somehow. Might take a few years, but I'll try. That would be interesting. Yeah.
Okay, we're gonna go to Joel and then Catherine and then cut it.
Yeah, I'm just wondering if there's a particular GPA level that we should be looking out for. Does it like plummet the performance in an astro class below a certain GPA, or have you looked into that?
So I got my hands on the data set not too long before I had to submit slides. So I haven't done the 100% complete analysis yet. But typically, from what it looks like initially, it would be somewhere along the lines of maybe slightly about 2.5. It might be that mark. This is right around like the C, D kind of range. Yeah.
Yeah, Catherine.
I was interested in the influence of the class makeup on the success of the students, in the sense that when I was at Wesleyan University and taught this sort of class, then there was a rule that only non-science majors could take the class. At Columbia, that rule is not there. So we have a mixture of science majors and non-science majors. And I've always felt that sets up a little, it's different. I mean, I would teach to those populations differently, and having them mixed in the class, it seems to me, maybe it could go either way. Maybe it raises the level of discussion in the class and everybody gains. But on the other hand, maybe it's more intimidating to people who may not have seen science and math for 4 years. I'm just wondering if there's a way for you to study that.
Yeah, so the way to go about that would be doing some sort of a qualitative and educational psychology kind of background for that. But my train of thought would be teach to so that everybody can understand. So in my classes, I do have a mix of science, STEM and non-STEM majors. So I teach to the students who need more help in that area.
Yeah, me too. Yeah. In fact, I tell the STEM students they shouldn't be here. But there we go. I'm so mean.
Yeah. Yes. But yeah. So every institution is different. Sometimes the only astronomy course is the general studies course. Yeah.
All right. Let's thank Zach once more.
Thank you. And find me if you want to talk to me more.